before the show, I wanted to introduce you to the people to make this show possible. You know, we spend several weeks putting together the experiments, and the person who's most responsible for this is Michael Thomason. Is Michael? Oh, he's here. Michael is our physics wizard. And he developed most of the best demonstrations we're going to do today. And if you like them, then come back in 8 or 10 years and enroll in physics at CU, and you can do even more. and then we've also helped from 2 people from our group who use lasers every day and so are experts in this area. And those are Erez Gershkurin and Pat Cole. And we'll also have some help from Gitte, who will help us too. And today is a particularly appropriate day for lasers and light show. Anybody know why? Because it's the winter solstice, exactly. So we all need some light, some more extra light today. And we'll send people home with a little gift, a light stick or hologram, and we'll also ask you guys to sing along during the show, so hopefully everybody's in a holiday spirit. So we'd like to start the show by talking about and demonstrating all the different ways we can make light. So in nature, what would have been the first exposure of people to light? Fire, that's a good example. Sunlight, exactly. Any other way that nature makes light? We'll get to light bulbs, but in nature. Lightning, exactly. Okay, so we'll do a demonstration, one of Michael's demonstration involving lightning. So we'll need Erez to control the lightning, and we'll need a very brave volunteer to, sample the lightning. Okay, how about I get you? Yep. And so what we'll do first is show.
What's your name?
Colin.
Okay, so Colin and I will stand back over here first, and we'll get the lightning going, and then we'll walk close, and we're going to get the lightning going. You heard that? Yeah. Using a Tesla coil, and we have a device here that charges the ring to very high voltage, and that causes a discharge in the air, just like in a lightning storm. And Henry's going to Erez will turn on so we can all see the lightning, and then Colin will move close so that the voltage that generates the lightning will also cause this fluorescent bulb to... So, hey, Darth Vader, you come over here for a minute. Yeah. So we're just going to look at the lightning for it. So,
You want to wear?
Yeah. It looks better on Colin anyway.
Yes.
That's right. Yeah. And it's matching and everything. Okay, so let's first just observe the lightning. Yep. And okay, we can walk a little bit close and try and just hold this up. So we've got a nice light over here. Thank you. Okay, and so now we want to do an experiment. Thank you, Colin. The next experiment will involve a little bit more pain, so we're going to get so Henry and I will do it. So this experiment is going to involve conducting that voltage difference that causes the fluorescent light to light up through our bodies. So that means Henry has to step a little bit closer to the lightning for this to work. So
It is
so we'll get Erez to start it up, and now if okay. So did you notice that? The second fluorescent light only lit up when we held hands, for those of you where we went a bit too quickly. So thank you. Yeah, if you want to, yeah.
So would anybody care to speculate on what's going on when lightning happens? Just There's a hand back there in the red dress. It shoots out of the stick. Yeah, that's true. So that what's happening when lightning happens is that we're generating a very high voltage, and that makes particles in the air move very fast. They get attracted to the voltage, and that turns that energy that's going into that coil into light.
Okay, so what is there? There's one other kind of light that is generated in nature. Give you a hint, maybe. Well, maybe fire. Yes, we don't have we'll have an example of fire later. Yes, in fact, several examples. So I won't do a demo now on fire, but fire is correct. Firefly, exactly. So you can also generate light in nature through chemical reactions, and we'll need 4 volunteers to demonstrate that. So, okay, so let me grab people from, you want to come on up? And we'll get here, and then maybe some people from the back, maybe one person from the very back here. Yep, in purple, that's great. And then somebody, let's see, we should get somebody from up here. You want to come from up here? Yeah. So it'll take a little while to get people down, but we'll manage it. And so what we'll show, but let me assure you, we have a small gift for everybody, either a light stick or a hologram for everyone to take home. So we'll have something for everybody at the end of the show. So what I'll get, what's your name? Erin and Alex and Erha and John to do. I know, is to stand out here in the front so people can see and hold and crack the light sticks, and let's watch them as the chemical reaction happens and generates the light. Yeah. Okay. So that's just a pretty. If you crack them a lot, then you can make the chemical react in all the regions of the light stick, and it'll glow really nicely. And we tried. They last a couple of days, and. Yeah, that's right. They last longer if you put them in the fridge. You're right. Okay. So that's the kind of chemical reaction that produces light that are in the fireflies or in water in certain. Thank you.
How does, if you put it in the refrigerator, how does it?
Do we have our chemist? Is David still here? The question is, so why when we put the light stick in the refrigerator does it last longer? It slows the reaction. So it slows the chemical reaction down. So we have it from our expert chemist. Okay, so thank you. You can keep that, yes, and we'll have more of those to give out at the end of the show. And then somebody had mentioned light bulb as being a source of light that's not produced in nature. And we have a demonstration here to show you how the light bulb produces light. And so what we're going to do here is we're going to run some electricity through this wire. So here we have some electrical connections to a wire that's strung across here. And then what you'll see as I begin to run electricity through, I'll answer your question in just one moment. As I begin to run electricity through, the wire will start glowing first, barely red, and then white. And then because this wire is exposed to air, eventually the wire will actually break. Of course, it doesn't happen in our light bulbs because the light bulbs are in a vacuum, exactly. So let's start. Now, I had a couple of questions here. Maybe I should answer first. Sorry? No, there won't be any loud noise with this demonstration. Later on, we'll have some noise, but not on this one, okay? So you don't have to cover your ears on this one. Okay. We'll warn you. That's a good point. Okay. So now, Yeah, if somebody wants to, I could get help turning up the current, but you have to turn it really slowly. So is somebody able to turn very, very slowly? Okay, you want to come up? So, yeah, good. And what's your name?
Leo.
Leo? Okay,
Leo.
now. Okay, so now we'll turn, so I want you to hold this knob with me, that's right, and we'll turn it very, very slowly. And we'll watch the wire at the same time. That's right, very slowly. We watch the wire very slowly. And then at some point, it might start glowing very...
I can hear it.
Oh, wait, no, not that fast. Yep, just in case. Oh, you see it? Yeah. And now it's glowing red, and now we go slowly, slowly, slowly.
If you touched it, you'd get burned.
No.
No. Sorry.
And now what's happening? You see it's getting so hot. It's beginning to... Now it's getting as hot. It's bright as a light bulb now.
You notice the wire's getting soft now and it's starting to reshape. So,
Oh, that's nice color.
yep, it's starting to melt.
Yeah, so I think we could barely make it melt, but... Whoa, okay. Thank you, Leo. Good. Yeah. They are pretty much melted. There's a little bit left here. And, whoops. Now, whoops.
I'll take this wire.
Yeah, so it's just a regular piece of wire, and it's cold because it's very small. It gets cold very quickly. So what other kind of light sources beside light bulbs do we have? You can see some of them here. Anybody know what I've got here? That. Yep. Yeah. Flashlights and lasers, exactly. So let's beam some of these up to the roof so we can see the difference. So we'll need some help with that. So let me take some people from back here. Yep, you want to come? Both? Yeah. And, oh, okay, good. Yeah, so you pick people too. And let's see, so we have a girl, a boy.
Shirt back there. Yeah, you.
Yeah. And we'll need 5 people, so let's pick, so at the very back row there, yep. And how are we doing now? Okay, so I'm going to hand out some things randomly now, here. So how many people? You want to stand up front here? Okay, you can take this, that's right. Okay, and I think we have 5 people now. So you want to stand up here? Okay. Okay, so let's stand up front here. And what we'll do is just look at the difference between these different light sources. So what's your name? Leah? Katie and Matt have laser pointers, and Ian and JT have flashlights. So let's beam them all up on either the screen or the roof. We can try that. Let's do it maybe on the screen and look at the difference between. Okay, so so we have some nice holiday colors. Now, yeah, that's right. They're making us a light show. Now, did everybody get their pointer on? Okay, so this one you hold. That's right. And maybe I'll turn this one off because it's confusing us all. So can you see the difference then between the flashlights here and the laser light. So what's the big difference that you can notice between the laser light and the flashlights? Well, there's several differences, but what are they? Okay, I'll have to turn the lights on a little bit so I can, so how about, what do you notice about the difference between the flashlights and the laser light? Correct. So the laser beam is much smaller than the flashlight beam. And that's one property of laser light, that it doesn't spread out or diverge in the same way as the flashlight beam. You're right, the flashlight is a light bulb. And then there's another very obvious difference between the flashlight light and the laser light. Anybody want to, you know? Mm-hmm. Okay. And do you notice about their colors? You want to? Yeah, that's right. So the laser light has usually a single color. It's usually what's called monochromatic. Okay, and it stays. It's very directed and pointed and stays, and it doesn't spread out. And so we have a demonstration of that. So thank you very much. Now I'll take these. Thank you. And because the laser light, thank you. And because the laser light stays directed, it's useful for many things that, for example, the supermarket scanners, or for security, because it's hard to get by a laser beam, because they're very easy to scan. And so Henry's working on a demonstration that will show us how they might be used in a security system. So what we assembled here was a laser doorway or a laser portal. We're not sure where, maybe it's the North Pole, but as I turn the light down, you can see the green spots and maybe the red spots if you look very carefully. And right now you can't really see the laser beams, isn't that right? And usually, when we were playing with the laser pointers, you see the laser beam best actually when it hits the screen or it hits the roof. Does anybody know why? Because the lasers are infrared? Part of the reason is that the laser might be in a wavelength region that's hard for your eye to see. But the other reason is, have you ever noticed on a foggy day how it's much easier to see the rays of light, for example, from the street lighting? And so fog makes it possible for us to see the light beam so much better, because the particles in the fog scatter the light into our eye, and otherwise the light stays going in a very specific direction and never reaches our eye, so we can't see it. And so I think Henry at the back here should have, or we can get help. We could. And anybody wants to help us make some fog?
It's a little dark in here, so. Over at the back there in the blue shirt, yep.
In fact, we could have 2 volunteers. We could have a second volunteer who might be willing to walk through the laser portal. Yeah.
Okay, so
let's. Okay, so yeah.
Just hold the spots here. Can you handle it? Then the other finger, push that.
So
point
since
it
the laser
here.
beams are hard to see, I'm going to turn the light down now, and what we're going to do is generate some fog so we can actually see.
You can move it around a bit.
We can see very nice holiday colors. So clearly a fog-making machine is a necessary piece of equipment for any respectable spy. Because you would need to know this, because you can't really see the beams unless you have your fog generator. And so next, if we could have our volunteer, can you stick your arm in the beam and should he do it? Yeah, okay. And just make a circle from it
You
so
can
you
put
can
some fog
do
in
some.
there too.
Yeah, so he's playing a little very nice light
Oh, is it?
show with
You
his
have to wait
hand.
for this
And
slide
then
to go off and
you might
start
want to,
working.
do you want to try and carefully then step through? You, lovely. Okay, so, and he lived to tell the tale, so that's very good. And he was not transported to the North Pole either, so that's good. So
Okay, thank you.
we'll put this demonstration on at the end of the show. So if you want to go see it more carefully, you can come back down and see it later. And we've been showing you some laser pointers and such. And one thing I wanted to show you was, so the laser pointers, they're not quite the smallest laser in the world because the lasers in your CD player are much smaller, but they're pretty small and handheld. What I wanted to show you here was an example of what used to be the largest laser in the world. So you can see it's in California at Lawrence Livermore Lab, and this is just one section of that laser. And you can see how big it is because if you notice here, this is a person standing up. So that laser fills the whole building. But that laser was used to do laser fusion, so it needed to
We
be...
can't do demos with it.
Correct, correct, yeah. Not... So let's summarize then what we've learned so far. We've talked about laser light, that it's directed, it stays propagating in the same direction so much better than light from a light bulb or a flashlight. And it also usually is monochromatic or has a very specific color, either red or green. And the next we'd like to talk about the colors of light. And so so can people call out to me the colors of the rainbow? Correct. RGB, correct. Can we get the projector turned off for a little while, just so we can get the gray? Thank you. Great, thank you so much. So the reason we wanted that off is we wanted to show you this little demonstration that takes the light bulb from a projector, and then we'll straighten out our thing. And then we'll hang a diffraction grating over it just to make the colors in the rainbow. So they're very beautiful. And so this is an example where we're splitting white light into its component colors, just like the raindrops do to sunlight when a rainbow is generated. And we can either split light into colors, or we can make white light from its component colors. And so we need 3 people now who'd be willing to make white light for us. So let's grab some people. Now, I know I almost... Do you want to come down, Jan?
What's your name? JT. Oh, wait, you already did. No, we need new people. How about you? Emily, come down.
So
And, okay.
Henry can control the lights, and we'll need to come
Davis.
back here to make white light. So I'm going to give you the... See now, did we... Okay, and so I want to give you this light bulb, and I want you to shine these lights then, thank you, on the screen. Great. So you're green, and there we have red, and there we'll have blue. And we'll want to stand close up here so we can...
Wait, so
Yeah, you figure... Great. So correct. Great. Okay, so let's stand close up together so we can sort of irradiate the same spot. Excellent. And then you're blue, green, red, okay? You remember that? So we'll do the color combinations then, and maybe we can dim the lights so we can see this
Sure.
nicely. Great. Great. And so you notice that when we overlap all the different colors, red and blue and green, we get a nice white light. Let's see each one of these colors individually. So everyone turn off their lights now. And great, great. And now, so let's see green. That's definitely green, isn't that right? And then let's turn on red. Definitely red. And then we have blue, definitely blue. And let's start to mix colors. So what should we get if we mix red and green? Yellow. Okay, so let's try that with the two. And that's a passable yellow. And what will happen if we mix red and blue? Purple. Okay, so let's try red and blue. Yeah, so we can get purple in the region where they overlap. And then the final one then will be blue and green, and we should get, well, so what color is that? A blue-green, correct. Blue-green or, yes, turquoise or cyan is what it's also called. Thank you very much. So maybe we'll get the lights on again.
Ow, that hurts.
Oh.
I can't.
And so thank you. Your name was?
Emily.
Emily and
Thank you, Emily.
David
Ian.
and Ian. Thank you very much.
David and Ian. Thank you
Wait,
very
no,
much.
careful. Thank you. Okay. Now, there are other ways of making different colored lights, and some depend on, in this demonstration, all the colors were on at once, but we can have other situations where the colors are being blinked so fast that your eye can't pick them up. And so we should get a person to do this demonstration. Okay? You want to come? Yeah. So what I want you to do is hold this very still, okay? Okay, so let me we'll dim the light, and your name is? Jill, okay. So hold it very still, and show it to everybody. That's right, keeping it very still, okay? And so what color is that? Yellow, okay. So now you could try holding it down here. Down. Oh, okay. If you hold it up really high so everybody can see. Okay? And so now, start moving it now. And so what colors do you see now? Correct. Red and green. And so what's happening in this little LED is that the red and green are being flashed alternately, but most of the time your eye isn't fast enough to pick that up, except if you stop and if you blink your eye or if you move your head very quickly, you can actually see it. But most of the time you can't. So thank you, Jill. And then we have another example of that. If we can get another helper. You want to come? Okay. And so who have we here? Braden. Okay. So what Braden will do is hold these two white light sources. I want you to hold them very still. So you'll have to, well, maybe we should, okay, you can do, okay, fine.
Yeah, I can't get on.
Okay, I'll turn that on for you, so. Now, hold it very still, and then hold that one on. And then, so what do you see now? One is blinking different colors, correct. So now, correct, okay. And so now, but when you hold them still for a moment. So when Braden holds the light sources very still, we see white light coming from both of them. Isn't that right? When he holds them very still. And now, I know it's hard to keep on. And now, shake your hand. And so what do you see on one? Yeah, that's right. Whereas, yeah, we're making you guys work very hard this morning. So that's a beautiful, yeah. Thank you.
No. We'll get to
Thank
all
you.
of that.
And so that's just different ways we can make white light from light of different colors. But of course, there's also colors, and in fact, different colors absorb light differently. And you know that because if you had a black car and a white car on a sunny day, which surface would get hotter? The black, correct. And so what we're going to try to do here is show you how different colored Mickey Mouse balloons absorb laser light differently. So Henry's going to start setting up that experiment. This is a popping experiment, correct, if it works right. We made a grave mistake last night that we popped all the black balloons. So that was a very grave mistake, but we'll try it with the blue balloon this morning. The blue balloon, correct. Good.
Okay, so do we
So-
need a volunteer for this? A brave volunteer? Okay,
Okay.
let's
Someone
see.
from the back.
In the red shirt back there. Great. Okay, so what we're going to,
And what's your name? Scott. Scott is going to wear these very fashionable glasses for this, very
Yeah.
cool pink glasses for this experiment.
what we're going to show here is that different colors of light interact very differently with other colors. And in fact, the green light from this laser, which you can see here, will behave very differently, will be absorbed very differently when we hold the balloon in the way. So what
Is that
we're
microphone
doing,
working? No. Okay.
yeah, the problem is I can't
Okay, okay.
hold the balloon.
So what we're going to try to show you is that the different colored balloons absorb light differently. And so we should be able to pop some of the balloons and not others. And this definitely worked last night with black balloons. So we have to see if it'll work now today with the blue
And
balloons.
move it into the beam.
And so what we have here is a laser beam that's focused.
Okay, move it.
Oh, the blue balloons do not pop as well as the black balloons for obvious reasons.
Let's,
So we could cheat a little
hit the nose.
and hit Mickey Mouse on the nose, which
Do you want to try that again?
is black, which is why the balloon pops.
You can just let go of that
we're-
one. It's fine.
We're going to try Mickey Mouse on the nose again. Actually,
Move it
maybe,
up just a
sorry.
little bit.
okay, I'll get out of the way so people can
Move it
see.
Well, I think maybe we should quit while we're
Ahead, okay, so
here.
we popped one. Okay, we can try and find a really black part here. Yeah. The other thing is we could try some direct. Maybe we'll try some at the end. We'll try some directly. Okay, thank you. Thank you.
Here.
Yeah.
Have a balloon.
Yes, we'll try and give everybody a
Well,
gift going
pass
home, a
some out
balloon
here.
or a light
That
stick
would
or a
be
hologram.
great.
Wait, where's it? Yeah. So, the other thing we wanted to show you is that there are colors of light that are beyond the range where your eye is sensitive. So your eye, of course, we're very sensitive to the colors of the rainbow. But there's light that has a wavelength shorter and longer than the colors on the rainbow that we can see. Does anybody know what they're called? It's what you wear sunscreen to protect you against. Which is? It's the ultraviolet light. Correct. So we're going to do a demonstration to show you ultraviolet light and the type of light that can also make you warm, which is infrared. Correct. So we'll show you both ultraviolet and infrared light. And so let's first do the ultraviolet light. So the ultraviolet light is very good at making things glow. And so what we have here in the beaker, although we probably want to add more to it, is some laundry detergent. And there's some nice chemicals in the laundry detergent that, when exposed to ultraviolet light, will glow. And of course they're put in the laundry detergent so that your white clothes come out whiter than white, and that they're very bright in the sunlight. So you can see, okay, if I close this, yeah. So there's just the laundry detergent. I don't know what brand it is.
You know, this brand doesn't work.
Power brand laundry detergent, showing that it glows. Okay.
Here, it looks better on the canister. Okay.
And the next experiment we're going to do is to show you infrared light. And for the UV bulb, you only saw the blue and purple or violet parts of the spectrum, and you actually never saw the light that was causing the detergent to glow. It will be more obvious with the infrared laser we have back here. And infrared lasers are often used for cutting and welding because they're very good at heating things up. And we'll see that when the infrared laser hits a piece of wood. We'll know why they're used to cut metal in factories and such. So Henry's going to turn the infrared laser on and tell us and we'll know when the infrared laser is on because the brick will glow. So can people see the glowing brick? And I'm going to turn down the light so you can all verify that you don't see any laser beam. Henry, can you point out the laser to them, to everybody?
This is the laser
So
here.
the CO2 laser it's carbon dioxide gas.
It's shooting
pretty
out
small.
from this and hitting the brick.
It's shooting from, let me try and point it out to people. It's shooting from, so the laser is here. Can people see that here? There's so the infrared laser is there where my green laser pointer is hitting. Do people see that? Okay, and then the glowing brick is here, and there's nothing attached to the brick. You can take away the frog generator from behind it, Henry, just so people know there is nothing causing that glowing brick except for the infrared beam. And you cannot see the beam now, and if I turn the light down, you don't see any laser beam in between this infrared laser and the glowing brick. Now the infrared light is very good at warming things up, and we're going to demonstrate that by using a piece of wood and making a little fire. Wasn't the first way people made fire, because of course they didn't have lasers back then. They didn't have lasers until 1959 or 1960. So now what we're going to do is put the piece of wood in the infrared beam and see what happens.
This is Michael.
And Michael has
And what you
bravely
want to do is
volunteered
just hold it
to
like this and slowly
do some
pass
laser
it through
cutting.
the beam.
No, it will not be loud. So do you see that? Yeah. So clearly, this is something you would want to do with a piece of wood and not with your hand. Yeah.
You can try and
That
light
is fire,
something
yes.
with it.
The infrared light is heating up the wood so much that it's catching fire immediately, but it's very localized, and that's why the CO2 laser is so very good at cutting, because it can very precisely make a cut just in one place. And you can turn down the power with laser light so it doesn't catch it on fire, because clearly you would not want something to catch on fire if you were doing laser surgery or something like that. But you would turn down the power in that case. In this case, of course, we want to show you the ability of the laser light to catch something on fire.
Okay, thank you.
No, cut all the way through. We'd have to wait a while with this laser, but there are bigger CO2 lasers where you could cut it all the way through just like that and cut metal through just like that. Okay, thank you. Excuse me?
Okay. Oh, show us the
Oh, show
wood.
the wood. Oh, okay, yes. Yeah. So, of course, laser scribing also works because of...
Pass it around. Hi, so for this section of the show, what we're going to do is talk about some of the ways that lasers are used today. Does anybody have ideas? What do people use lasers for? pointing out things, and we've done some of that with our laser pointers. What else? Surgery. That's right. And we've sort of shown that with the balloon that you can use lasers to very selectively cut things. Orange. Shaping? Yeah, you can, it's similar to surgery, right? You're machining something.
Security?
Security, and that's similar to what we did with this doorway here. If you interrupt the light beam, you can see that very easily. Cause chemical reactions, that's right. That's something we do a lot in the lab. Laser shows, definitely. Yep. Making CDs, yeah, and also reading CDs. And targeting, yeah, for targeting for rifles, that's right. It's great. I'm looking for a certain answer, and we're getting everything else along the way. Communications, that's the thing I was looking for, because I wanted to show you a little bit about probably one of the biggest uses of laser, which is for the internet and for transmitting data. And we have a couple of examples of that. I'd like a couple volunteers, so
Monica?
and blue shirt there. Yep, you. What's
And
your
then-
name?
And then
Greg?
A girl then for,
I think we need two people for this, don't
oh,
we?
okay, we could, okay.
And your name is? Brandon and Greg. Thank you very
Okay,
much.
so first
So-
let's have Brandon show the light beam when I turn.
Okay, I wanted to have them point it, but it looks like it's already pointed.
It
Is
is,
that right?
yeah.
Should I unpoint it?
No, this is good, but. it's-
Okay, so what we have here is a light beam that's coming from this source here, and you can see it against my hand, although it might be a little difficult from this angle. And it's coming out to a device over here.
Do you want to spray the light and you might be able to see the beam if you spray the light in?
The first thing we're going to do is, okay, so you have a comb. Can you interrupt the light beam with the comb here? And Brandon and Greg, could you come here and adjust this? We're trying to look for a signal, a Morse code here. Oh, there it goes. Okay, so move the comb back and forth. So you notice what we're doing here is that Brandon's comb, when he moves it, is interrupting a light beam, and then there's a receiver here that converts that light beam into sound. And of course, this is a very simple example, but we can also
Spray the water?
do
water,
things
yeah.
like spray water, so Greg can interrupt the beam in a different way, and it should make a sound, but maybe it needs to be adjusted just slightly. Keep trying it. Yeah, okay, that's good. So here we're interrupting it just in a different, more random way. So this is a good way of making so-called white noise. But the other thing that we can do is actually feed a signal in to this side and very quickly change the brightness of that laser in a way that can transmit information. So now Margaret's going to hit the button here, and with any luck, so you can walk into the beam and interrupt it. you notice that just by putting my hand in the beam here, I can stop the music and start it. So this is very similar in concept to what we use for for transmitting information, except that when we transmit information, for example, over the internet, we don't have a clear line of sight. So the way that we do transmit information with light is through something called fiber optics, and that's by guiding light using a material. And the way that this is done in actuality is we use very thin strands of glass, but we have a great demo here that actually guides light through a stream of water. And I think I'll get a couple new volunteers. Thank you very much, Brandon and Greg. And in the purple. So what's your name? Corey. Courtney. Okay, Courtney. What we need you to do, it might be a little difficult. Can you reach this cork? Do you want me to lift you up a bit? Okay, so Courtney is pull out the cork. Thank you very much. And what we should be able to see here is the light guided through the water. And what's happening here? Can anybody speculate? I can't see anybody, so you can just shout, but
The laser's following the water.
the laser's following the water, and it's following it because when it encounters the edge of the water, it reflects off it. And if you can get a very good view of this, you'll see, in fact, that you can see a beam reflecting off in the inside of the water jet here. So I'll plug this before it makes a big mess. Now, the way that this is done in communication systems is through optical fiber, which is a very thin strand of glass. And Margaret is setting up here to show what happens with optical fiber. We have a green laser. How's it working? And this is a little bit delicate, which is why we can't do a volunteer. Okay, you're getting it. I see it starting to glow. Ah. Okay, so I think that's probably as good as you're gonna get, isn't it? Okay, there. Ah, great. Great. So, okay, what you're seeing here is that we're guiding laser light inside this optical fiber. This is a spool. It has about 1/4 mile of fiber in it. And the idea behind communicating through optical fibers is that you guide the light through here. And in fact, you can guide it all the way across the ocean. And at the other end, so you could be in New York, you put light in your fiber. In Amsterdam, the other end of the fiber gives us this light. And then if we modulate this laser by turning it on and off, we're in fact communicating. So I think I'll just leave this because this is a pretty demo.
So next we wanted to show you another very nice use of laser beams, which is to use them to make holograms. And so we're going to set up to show you a hologram. And we also wanted to show you the use of lasers to make some very nice patterns. Of course, there's more information than just a simple pattern on a hologram. But while we're setting up the holograms, maybe we could have 2 volunteers to show, so we can show the use of a laser to make a pattern. So let me, in the red striped sweater from this side, and then from over here, maybe with the orange. Great, yeah. Yep, yep. You want to come down? Okay, so I want you to hold this for a moment. And your name is? Mark. Mark? And your name is? Corey? Okay, so I want you to beam the laser beam, over. So point, the laser beam will come out this side. So you want to point the laser pointer this way and then hit the switch and point the laser beam, lovely. And then you do the same, that's Corey, that's right, and we should be able to get, yes, lovely. So we just have 2 nice star patterns that are very easy for us to make these very nice. They're called diffraction patterns, and we can make them so nicely with the laser beam because the laser beam will stay pointed in the same direction. And an even fancier use of laser beams then will be our hologram that Michael is setting up. Okay, so let me get the. Okay, so can you see the hologram there? So you can see the scientist, that Dr. Young, and maybe we can get the stars up on top so we can actually, yes. And so how we know that is a hologram and not just a projected image is as Michael rotates the hologram, you should be able to see the figure move with respect to the background. So you should see the Dr. Young's finger pointing in a different direction as Michael changes the angle. And of course that does not happen with a projected image. With a projected image that's not a hologram, no matter what way you move your head, the image doesn't change. But in this way, when Michael moves the hologram, you can see the figure move with respect to the background. You see? As you can see it very nicely here, as he moves the hologram, you can see Dr. Young change his position with respect to the shelves behind him. Did everybody see that? Yeah. So that's, no? Okay. So look at Dr. Young's head and look at the objects on the shelf right behind his head. And as Michael rotates the hologram, do you see Dr. Young's head move in front of the objects and from side to side? Did you see that this time? And that's the big difference between the hologram and a picture. When you take a picture, which is a 2-dimensional image, then as you move the picture or move your head, the picture doesn't change at all. But the hologram, there's much more information in it, and that's why we can see. And then we have either light sticks or little holograms to give people on the way home. So don't rush out too early. Yeah. Okay, but thank you very much. Thank you. Thank you, Michael. We're ready for the finale. We're ready for the finale, which is, will I show the view guys?
Yeah, sure. So for the finale, we wanted to try to do a demonstration that relates to the type of work that we do in the lab. And one of the big uses of lasers in a research lab is that you can make very, very short pulses of light. And what could you do with a very short pulse of light? Slow down atoms. Yeah, we do that. What other things? Morse code. Yeah, you could use it. Short pulses of light are used for communications. And well, what's the most common type of light flash that people use in their everyday life? Videos, television, cameras, right? What does a camera flash do? it stops the motion of an object so that you can freeze it in one instant in time. Now, this is an example of using a camera flash to see what's going on in a very fast-moving event. This is actually a famous.
Which one do you want?
Yeah, the first one. A famous sequence of photographs taken in 1887, more than 100 years ago. And these were done by Edward Muybridge, who was working in California at the time, and he was commissioned to take these photos at the behest of Leland Stanford, who's a familiar name now. But the reason is that Leland Stanford made a bet as to whether a horse, when he's galloping, whether his hooves actually leave the ground. And of course, you can't tell just by watching a horse move, but in this sequence of photographs, which was taken with a series of tripwires that flashed the camera, you can see, in fact, that there are some times in the sequence when the horse is actually completely off the ground here. And that was sort of the beginning of this field of using short pulses of light to illuminate how very fast things happen. This is an example of stroboscopic photography of a water droplet. And this is a very famous picture showing a bullet piercing an apple. Now, this picture was taken with a flash of light about 1/1,000,000th of a second in duration, which is about how short you need to stop the action of a bullet. Now, in the research lab, we're now using light flashes that are 1,000,000,000 times shorter in time than the one that was used to create this photograph. And of course, in that period of time, a bullet isn't going to move more than a couple of widths of an atom. But the things that do move in that time are atoms and molecules. So in our research lab, we look at how atoms and molecules move. And we have a demonstration. Actually, this view graph just shows the types of time scales that we can now look at in the lab. This is the shortest light pulses we can make. It's 10 to the minus 14 seconds, which is a few millionths of a billionth of a second. And just to compare that with the age of the universe, for those of you who know about geometric means, that there is as many factors of 10 between the duration of this light pulse and a time of 1 minute as there is between a time of 1 minute and the age of the universe. Now, we can't do a good demonstration with pulses of light that short, but what we can do is do something that shows how we can stop motion with flashes of light. Oh, I'm going to need help collecting tennis balls here. So what we're doing is shooting tennis balls across the room, and we're going to stop their motion. So can you pick a...
Okay, sure. So two people who feel very athletic this morning. Okay, come on. And let's pick someone. So at the very back with the long hair. Yep. So we're going to go get some.
So right now the lights are on. You can see the ball go from one end of the hall to the other. But now we're going to turn off the lights. And what you'll see is that you can, in fact, spot the tennis ball, hopefully at the same place every time. It's right about here right now. See it? And what we can do now is very much like what we do in the lab, which is change the delay between when the event happens and when the flash of light looks at it. So right now the ball is about here. I can continue to adjust the time what you can see is that we can trace out the trajectory of this ball just by repeating the process and taking these photographs. Okay.
Okay, so I think that's it.
There are a number of things you can see up here at the front, like this gateway here is pretty neat, and a few other things. But that's the conclusion of our show, and people can come down and pick up the freebies and